The next talk will be in English, obviously, and it will be about a very specific, a very special and very interesting topic. Frank Wunderlich-Pfeiffer he is a journalist, he works for golem.de, but he's also a podcaster, and he will explain to us how we could make space exploration cheaper. A very interesting topic. Please give a warm applause to our next speaker.
Okay, well, this seems to be on. Hello. It's not rocket science. I actually planned to give this talk without mentioning rockets, but then we got some new pictures and I ended up deciding against that. So just ahead of Christmas, SpaceX released new pictures from the new test spacecraft, and this is going to be the Starship test spacecraft. It's very much the same as Grasshopper that we had in 2012, so really don't expect this to be any more than an ugly test bed of a rocket that is flying a bit up and a bit down just to shake things down and see if the technology works. But the interesting thing was that they changed the technology they used to build this spaceship. And if you remember back 2 years or something like that, the SpaceX presented a large carbon fiber tank, a fuel tank that would be primary structure of the new spacecraft. And now he said, no, we're going to make it out of steel. Steel is known as a heavy material. Usually when you use steel, you have something like a huge building, maybe a ship or something like that. It's not something that you would use to build something as delicate and light as a spacecraft. In spacecraft, you usually use aluminum or carbon fiber or anything to make things as light as possible. And that's not what they did here, or so it seems. It seems to be that using steel cannot possibly result in something like a light spacecraft. But actually, you can use internal pressure within the tanks to stabilize it. And at least Elon Musk said, and I didn't have time to actually check that because it was just before Christmas and there was a lot to do in the meantime, that at high temperatures at least, steel is about as tough as carbon fiber, and the new spacecraft of SpaceX is supposed to withstand re-entry heats. They're quite high, and so steel could actually make sense. Well, why am I telling this story? Because it seems like steel is the right choice in this case. It reminded me of something else. The X-33 Venture Star, and this was supposed to be the next space shuttle back in the 1990s, early 2000s. Kind of looks like the space shuttle, and it was supposed to be single stage to orbit. Now there's a lot of things wrong with this whole concept, especially because it's single stage to orbit. The rocket equation does not take kindly to people trying to put something from the ground up into orbit. There are a lot of rockets that could actually do it. You could take a rocket and without any kind of staging, you could put several tons into a low Earth orbit. But it doesn't make sense because you can put a second stage on top of it and double or triple the payload even for low Earth orbits. And you couldn't reach any higher orbits with a single stage spacecraft like this one. But the reason why this one never flew, this was supposed to be a 1/3 scale model of the real thing, was something else. And we will talk about that after a little quote of Richard Feynman. Yes, reality is an important thing, and public relations are not quite important enough to go beyond the limits of the laws of nature. And single stage to orbit doesn't quite work. This demonstrator here was almost finished. All the components were there. And the problem was with this large blue thing. That's the hydrogen tank. These hydrogen tanks, you see it's two tanks, and there are two sections to it with a lobe in between, and it's a very complicated shape. And you wouldn't use that sort of shape in a normal tank. And they decided, well, those tanks, they have to be extremely light because it's supposed to go to space. It has to be extremely light to go to space. And so they made it out of carbon fiber. And they ran into trouble. They couldn't get it tight. They had leaks all the time. And also, it was not as light as they thought it would be, because a shape is complicated, and carbon fibers are actual fibers, and they are only strong in one direction, in the direction of the fiber, not perpendicular to it. And so they ended up using a lot more mass than they would have thought, especially in those lobe areas. This was so obvious to the engineers that there was a group of engineers within the company that built it, that they built a second tank, and they made it out of aluminum alloy. And the tank itself was heavier than the carbon fiber tank, but the lobes, they saved so much more weight on the lobes that it came out to be almost the exact same thing. But that was when the project was cancelled, because essentially it wasn't high-tech enough. They were so concentrated on on proving the principle of carbon fiber technologies for cryo tanks that they canceled the project in the end, which is quite a difference compared to SpaceX, who just thought, well, we can make it out of steel, and steel works, at least. Steel is not the first time that it's being used. In fact, this is the factory of the Atlas rockets, the early Atlas rockets. And this is shiny material, and it's actual steel, and those are the balloon tanks. They're under pressure, and if you go search on the web, you can find a nice video how they don't work. There's a video where one of those rockets is upright, and it loses pressure inside, and it just collapses like a tin can without pressure inside of it. And the way this is actually a very nice technology. It's pretty light, and it has been used again. It has been used again in the upper stage, the Centaur upper stage, also for the Atlas rocket, and they used steel tanks. This is the hydrogen steel tank. And this rocket stage is extremely light, even for today's standards. They kept building this stage since the 1960s, and Centaur stages are used to this day, and they still use steel because the balloon structure is quite light. In fact, it's what is today one of the lightest upper stages there are. I mean, I'm not going to complain too much about the Ariane 5 upper stage, which is a huge compromise and really inhibits its performance, but we'll come to that. It's a very simple material, and it has a great history. But if you want to build something cheap, you better build it in large numbers. Atlas rockets were built in large numbers in a factory like that, and you can see, yes, they had it down to the science, to a real factory, but there's a reason for that, and that reason is not space exploration. Atlas rockets were used to go to space. First American astronauts, John Glenn, who actually orbited the Earth, went on an Atlas rocket. And the actual payload of these rockets are nuclear bombs. And that's it's a huge tradition. Most rockets going to space usually had nuclear bombs on top of them. That's not just true for North Korea, it's true for almost any spacefaring nation that started out, except for exotics like maybe New Zealand, who recently started their own space program and started building their own rockets. They actually just went to space and never had nuclear bombs on top of them. But if you replace the nuclear bomb with an extra rocket stage and a satellite or a space probe, you can get it to orbit. And essentially what NASA did here was to use the surplus, the production facilities from the military to build their own rockets. Obviously, they built about 400 something rockets of this type, and they didn't quite need as many of those for spaceflight. Some of them were actually scrapped, a lot of them during the shuttle program. If you build so many rockets, you can build them cheaply. I think their production cost was originally something like $6 million, but there's a lot of inflation since that time. They were quite cheap anyway. And that's because of mass production. The problem with mass production is that, especially these days when you have larger rockets, and we have, for the first time since 1990, since the end of the Cold War, we have launched worldwide 100 rockets this year. That is not very suitable for mass production like this one. So the alternative is, instead of building the rockets in mass production, you can at least build the most important, most expensive components in mass production, and some nice examples of those are, of course, the Soyuz rockets, where they built the burning chambers and the nozzles, which are delicate parts, really en masse. Every Soyuz rocket, when you look at it from behind, has 20 such burning chambers and 5 sets of turbo pumps to deliver the fuel to them. And of course, we all know about the Falcon Heavy, 27 engines in the first stage. Having so many small engines means that you can build one engine every 3 days or something like that, and that really cuts down on production cost, especially compared to other rockets that are more current. ESA did the same thing. This is an Ariane 4 rocket, which was back in its day the cheapest rocket there was, and really disrupted the transportation of satellites into space as much as SpaceX did back in the 2000s. So ESA, with the Ariane rockets, the early Ariane rockets, really changed the game there. And they did it by putting a lot of identical and small engines. These are 8 Viking engines. In the first stage, there's 1 Viking engine in the second stage, and there's an upper stage that is fueled by hydrogen and a different rocket engine. It's very much the same concept as SpaceX used, and for some reason, they forgot all about it. Next rocket was Ariane 5. Ariane 5 consists of 2 solid boosters, one big engine, the Vulcan engine, and a large central stage, and an upper stage with yet another different engine. These rockets are built and launched about 6 every year. So every 2 months or so, you build 1 engine. That's very different than building 1 engine every 3 days. And that's what makes it so expensive. And if you there are some TV documentaries where you can see the production process of these engines, and there's a lot of handwork. There are, for example, about 500 injection nozzles inside of this engine, and well, there are 2 or 3 engineers in a room, and one of them is watching the other one while he is taking each injection nozzle and screwing it into the plate by hand. There's not a lot of automation you can do when you build 6 of those engines every year and 6 of those rockets every year. And that's a big reason why this has become quite expensive, and it had to be subsidized. Each rocket launch of those is subsidized by about 20 million euros, just to not actually be competitive, but to be just not quite so expensive that it's worth to develop a new rocket, at least until SpaceX came along. Next rocket is going to be Ariane 6, and it's not going to be that much better, especially if you have a look. It's going to be in 2 different flavors. The one with just two solid boosters, Ariane 6 A6-2, and the A6-4 is the big one. And essentially, it's the same rocket, just with smaller solid boosters. But you notice the actual payload on top is 5 tons. This one is 10 tons, and you wouldn't think that somebody would come up with this idea and say, hey, that's a good idea, because the solid rockets are the cheap part of the entire rocket. So by leaving out 2 of those solid rocket boosters, you can reduce the cost of the rocket by about 20 million euros or something like that. But you lose half of the payload. While when you have a big rocket, when you use 4 boosters, you can get about twice the payload for a marginal price increase. I've been told that the A6-2 will cost about 40% less than the Ariane 5 rocket, so it's going to be about 90 to 100 million euros for a performance similar to a Falcon 9 rocket. That is about as expensive as, 50 or 60 million euros. It's not going to be very cheap. And of course, the A6-4 is going to be 120, 130 million euros. And it doesn't look like this is going to be a very nice prospect for being competitive. What also struck me is people are actually using this one. When you have 5 tons of payload that you can bring into space, but by just using 20 million euros or maybe 30 million euros in addition to that, you can double it. That means you're actually wasting a lot of payload mass. That means it's pretty expensive to get a satellite into orbit, but getting 5 tons more into orbit when there's a rocket already going can be quite cheap. And even whenever you use the small variant of this rocket, means that you're wasting a lot of money and a lot of space in your rocket. Another problem is, this is an outdated graphic, but the whole production is distributed all over Europe. This is actually a point of pride for the producers, so you can find every part of it. So this is the Vulcan engine, and you can see here where all the components of the Vulcan engine are made. This is actually no longer current because, as far as I know, the oxygen pump will be built in Germany, and they traded it for some plans that were later announced between all this, where Germany was supposed to build casings for this motor and so on and so forth. There's a lot of political to and fro. This is in Europe. This is the case in Europe between different European countries. In the United States, you have something similar between the different states in the US. And it really increases cost. Who would have thought? Vulcan engine, if you have a problem with thrust, well, what could it be? Well, maybe it's the turbine. The turbine drives the pumps for the fuel pumps, the hydrogen pumps, and the oxygen pumps. And so you call up Sweden, well, check your turbine. And maybe you find out, no, it has nothing to do with the turbine. It's actually the hydrogen pump, so you have to call to France. Or maybe it's the gas generator. In this case, you're lucky because it's also in France, but it could be the oxygen pump, and it's not actually made in Italy anymore, so you have to call Germany, and so on and so forth. And that's just for one engine. And if you have any problem with this rocket, you're very likely to have to call another company in another country, probably in a different language. And yes, it's a bit of a miracle that it works at all, but it works, but it's not cheap. And everybody in ESA is aware. If you talk to people who are working on these rockets, they know very well they could be much cheaper. Well, let's talk about a different rocket. This is the rocket that was used to launch the latest Mars space probe. This is Mars Insight. And you might think, well, it's a big rocket, but it's like a really small space probe. Surely this must be some figment of the imagination. Probably it's much bigger and the artist made a mistake. But no, it's really that small, and it's about, I think, 700 or 800 kilograms. And this rocket, the way it's configured here, could at least put another 1.5 tons more to Mars. So there was room. There was a lot of room to occupy this, and you have 1.5 tons. So what do? You put a different space probe maybe into it and send it also to Mars, because finally have a chance to get a big chunk of metal or something to Mars. Anything you want. What did NASA do? Well, they sent 2 small CubeSats to Mars, and they're quite proud of it. And I can understand that, especially the teams that built those, they are quite proud of it, and quite rightfully so, because it's the first time that a small CubeSat was sent to Mars so far away and transmitted data, and that worked very well. But what about the other 1.5 tons? As a matter of fact, you could have put at least 1, maybe 2, or even 3 additional landers on Mars on the same rocket. There's a lot of waste going on in this space. And we're not even talking about the price of this rocket. Yeah. When you have so much mass, you could change the way you build such probes or satellites. Because right now, the reason why this is 800 kilograms is because when they constructed a space probe, they tried to save as much weight as possible. And a lot of effort is put into every single satellite, every single space mission to save weight. Every kilogram counts, or so it seems. But if you look at a rocket like this, it's 1.5 tons that are wasted, essentially. So what was your point in saving all this mass? There isn't very much to it. Also, remember that a lot of rockets are built with, are launched not in a maximum configuration, so you could, with very little extra expense, increase the payload. Instead, you could choose a different concept. And right now, there are not many manufacturers that do this on a large scale, but there's one manufacturer that I found that I interviewed, where they do it on a small scale. This is it's Burn Space Technologies, and this is one of the satellites they built, and it doesn't show up very nicely here, unfortunately. It's a satellite about this big, 0.5 meter, weighs about 70 kilograms, and they actually launched one of those already, and it's a modular system. It's just a box. It's a box with lots of little components inside of it that can be put into different places. And this means that you waste a lot of weight, because when you construct a satellite, you have to make sure that all the mass is distributed evenly. And you have to look at every system that works correctly with all the other systems. And as soon as you have to change something, you have to essentially start the construction all over again, because you now have to shift the whole weight distribution inside of it if you don't want to waste any mass. What you can do is you can just put some weights into the satellite box and shift them around each time you have to change a component. And you can do this. And they do it by, for example, taking their batteries and putting them into a different spot. And the spot is already designated. It's not like there's it's not so tightly built that there's no room to put it elsewhere. They just made room for it. That means the box is bigger. That means that the whole satellite will weigh more, and you will need more mass to achieve the same goals. But it gets cheaper, because now you can have your box and build it for different configurations and just qualify it once. And when you have to change something, you change it, and you're not leaving the scope that you qualified your box for, your entire satellite for. Also, what they do is they use very simple technology. When you look at this is the camera, and it doesn't show up very nicely here, but if you see it in person, it really looks like somebody took a regular photo lens and put it into a satellite, and you could be forgiven for thinking that, because that's what they did. It's a photo lens that's about this big, 10 centimeters across, and it's enough that from a 500-kilometer high orbit, you can take pictures with a resolution of about 5 meters. In many other satellites, there are specially built optics just for this. But you can use commercially available technology, just like for common consumer-grade camera. But you have to check that it actually works in vacuum, because there might be some sealant, some lubricant or something like that that evaporates in the vacuum. And when it evaporates in the vacuum, there's a little fine mist might deposit on the lenses and fog them up or something like that. And you have to check all that. But you can make it quite cheap that way. This is also a very nice piece. This is the star tracker they used. Star trackers are essentially cameras that look at star constellations, and from these star constellations, you can tell that where your satellite is pointing. And what it essentially is, it's a camera, and a fairly small camera at that. And what they used is a little board, and this looks like the camera board you would have in one of your smartphones. And that's because that's what it is. They essentially used a camera board from a smartphone, put a different lens on top of it. Much better lens, higher, gets more light on the sensor. And the hardware cost is quite cheap. It's like a few dollars. The problem here is you have to do all the engineering, you have to do the software, and this is what costs the money here. Another example is reaction wheels. Reaction wheels are a wheel that you spin, and because you spin the wheel in one direction, the satellite will tend to spin in the other direction, and that way you can control how the satellite is pointed in space. And usually you would take a reaction wheel and make it so it works in space, in vacuum. That's a problem, because you have to have some sort of lubrication, because you have to spin those wheels, and they will touch something, and there should not be too much friction between it. Well, on Earth here, we have solved these problems. We have a lot of absolutely fine lubricants that can work for years on end, no problem. But in vacuum, it's a different story. So instead of trying to find a vacuum-capable lubricant or something like that, they just put a box around it, wasted another 1 or 2 kilograms of mass, and put air into it and solve the problem that way, which is a very elegant and easy solution to a problem that you would normally have to solve. especially when you look at missions like the Kepler Space Telescope recently, or the Dawn mission. They had huge problems because they were in vacuum, and in vacuum you don't get to have the luxury that when you have a static charge, it eventually dissipates. You know, you have an electric charge, and because air conducts electricity very badly, but at least a bit, eventually, when you have something that's electrically charged, it will well dissipate the charge, and it will equalize. When you have it in vacuum, this doesn't happen, and the only way it can happen is through discharges. And it turns out in these ball bearings that you have very small differences between the ball bearings and the walls of micrometers. And when you have micrometers, you can get extremely high field strengths just from small voltages, like 1 or 2 volt difference between the ball bearing and the center of the wheel, and you can get arcs. And these arcs can melt the ball bearings and cause higher friction. And they found out the hard way by essentially screwing up several missions after a couple of years, and they only found out by looking at when the reaction wheels failed in space, and solar storms. And the solar storms consist of charged particles, and they charged up the satellite and caused this arcing to happen. And I really like that kind of modular approach, even though it's much more expensive in terms of the mass, but it requires much less engineering, can be qualified much more easily for continued for new missions for reuse. Finally, I want to talk about 2 missions that really kind of took this approach from India. India has actually a fairly unknown but quite viable space program. And what they did, they sent one mission to the moon and another one to Mars. And what those are is essentially a satellite that they already had, like telecommunication satellite, and they made room for cameras and other instruments. When they sent it to the moon, this worked quite well. They had about 80 kilograms of payload in there, of scientific payload. When they sent it to Mars, they had a somewhat bigger problem. And the problem was it takes more energy to get to Mars. And the Indian rockets, the heavier Indian rockets, were not quite reliable enough when they started to launch this. And so they had to use a small rocket. And these satellites were built for the small rocket, but they were built to go to a geostationary orbit. Now it turns out, and the geostationary orbit is the orbit that you use for TV satellites, kind of orbit where the satellite just stays on one spot in the sky. Now it turns out any satellite that can do that, that can get into this kind of orbit, has enough energy and enough fuel to get to the moon or even get to Mars, because it's quite a demanding mission. The problem then is only to get into an orbit around the moon or around Mars. And so getting to Mars is not the problem. Getting into a good orbit around Mars, that was the problem. And actually, this is Mangalyaan, that's the Mars mission, only has, I think, 12 kilograms of payload on board because of that, because they really had to use most of the fuel just to get into any kind of orbit. Okay, I hope you have some questions so I can answer them. Okay.
Yeah, first of all, thank you so much for this talk. Hopefully, there are some questions from the audience. Please don't be shy. Yes.
Is this done? Hi, thank you for the talk. My question would be, you said that mass production of the rocket engines allows you to cut down costs. So why do they even use bigger engines?
The original reasoning was that you only have one engine, so only one engine can fail.
Okay, thank you.
That is essentially that was the reasoning they used for a very long time, and it was supposed to be man-rated, so people were supposed to go on these. Of course, it's also women-rated. It's a pretty old concept, so yeah, they still call it man-rating. And they hope to improve the reliability of the whole system. But it turns out that a lot of the rockets that actually used a lot of engines were just as reliable as rockets that used just a single engine in one stage. And Ariane 4 itself was a pretty good example for that. Even though I did a lot of talking to people from ESA and CNES and others, and a lot of people would tell me, oh, that's you cannot use 9 engines like in Falcon 9 rocket. That would be too unreliable. But actually, okay, in the Falcon 9 they had a different trick, and they made sure they could still launch they could have one engine fail and still continue the launch. Unlike Ariane 4, where occasionally they had failures. I think they had 1 or 2 failures of engines, and that actually aborted the mission because it wasn't made for that.
Okay, thank you.
Yeah.
Thanks for your question. Next question over there. And one reminder, you can also ask questions from the internet if you're watching the stream. So please contact our Signal Angel.
What type of justifications do the space agencies give for not filling up the payloads? Do they risk, satellites interfering with each other or anything like that?
In this case, they didn't give any kind of justification. Instead, they launched it from the west coast of the United States and said, look, it's the first time we launched a rocket from the west, an interplanetary space probe from the west coast of the United States. Of course, they could only do this because they have had so much performance margin. And usually you would go for the East Coast and launch the rocket towards the east, which is along with the rotation of the Earth, and get an additional boost of speed just from the rotation of the Earth. And they just said, well, we don't need that, so we can also launch it from the West Coast. And now they made a big deal of, yeah, it's the first time that we had an interplanetary mission from the West Coast, but it's quite disingenuous.
Thanks for your question. Next one.
Yes, thanks for the great talk. You were talking about the problems with friction and lubrication.
Yep.
And the interesting solution that you showed near the end of your talk.
Yep.
I'm curious, what kind of solutions did they use for friction other than that, other than putting it in a can that was pressurized? How do you prevent the evaporation of the lubricant, or do they use some method that doesn't use the lubricant?
I think they found lubricants that work quite well, or I think there are also ceramic ball bearings that they are now using. And they also have the added advantage that they don't conduct electricity, so you don't get the arcing that led to the failure of Kepler and Dawn.
So ceramic ball bearings don't need to be lubricated?
I think not. I'm not entirely sure, but I think they have vacuum-capable lubrication.
Thank you.
Thank you for your questions. I think if no one now is jumping up and saying, yes, I have another one,
okay,
then we would close the event. And thank you for your talk. It was incredibly interesting. All these awesome rocket science pictures, incredible. Thank you for that. So give a very warm round of applause for our speaker.